In this video, we present our paper, Urban Radiance Field Representation with Deformable Neural Mesh Primitives. Neural radiance field has achieved great success in past years. NeRF and its advanced variants propose to store the density and radiance information of a volume inside multi-layer perceptrons, MLPs, and adopt volumetric rendering for view synthesis. However, the limited texture detail recovery and the intensive computation limit the generalization to large-scale urban scenarios. More recently, researchers have identified this issue and proposed to combine neural rendering with explicit point cloud reconstruction to improve the efficiency. However, methods like point NeRF require dense point cloud and costly feature aggregation. In this paper, we aim to develop an efficient radiance field representation for photorealistic neural rendering in urban scenarios. The mesh-based representation is widely used in modern rendering pipeline due to its efficient nature. But the watertight mesh is hard to obtain in outdoor environments and the realistic radiance information is hard to be recovered. The current point-based NeRF methods have outstanding representation ability, but the rendering process is less efficient. How to combine the advantages of the both types of representation? In this paper, we proposed deformable neural mesh primitive. Given a compact primitive latent code Z from a learnt latent space, we adopt a pre-trained shape decoder to decode Z to a DNMP, an enclosed mesh with associated learnable vertex radiance features. By optimizing the latent codes, DNMPs can be deformed into various basic shapes, which can be used to compose scene structures. To represent the entire scene, we first voxelize the patchy point cloud reconstruction. Then we use a DNMP to parameterize the geometry and radiance information of each voxel. During training, the shapes of DNMPs are deformed to model the underlying 3D structures, while the radiance vertex features of DNMPs are learnt to model the local radiance information for neural rendering. Based on our representation, we achieve efficient and photorealistic rendering for urban scenarios. During rendering, given a view ray, we can efficiently obtain the interpolated radiance features from the intersected DNMPs. These interpolated features along with the view-dependent embeddings are then sent to an implicit function to predict the radiance value and opacity of each intersection. Finally, the rendering color of the view ray is calculated as the expectation of the radiance values according to the opacities.